Right, I now come to the sixth episode on differential equations, and I've labeled this particular little section Cauchy's differential equation, because I believe the solution of this was originally attributed to Professor Cauchy. So here's an example or two. The first one is x squared d2y dx squared plus ax dy dx plus b of y equals some function of x. The second is a similar one but of a higher order, x cubed d3y dx cubed plus ax squared d2y dx squared plus bx dy dx plus c of y equals, again, some function of x. Now, the thing to notice here is that the power to which x is raised is the order of the differential. So if you look in the first one over here, the x squared is the same order as the order of the differentiation of the order of the differential, which is 2, etc., etc. I think you get the idea there. It's not difficult to grasp, okay? Now, these equations can be transformed to linear equations with constant coefficients if we use the substitution x equals e to the u. Now, we've dealt with these equations in the previous episodes, okay? But in order to do this, you will need the following, which I've written up in red. And the first one is that dy dx under this transformation will equal 1 over x du dx. d2y dx squared equals 1 over x squared bracket d2y du squared minus dy du. And carrying on with that, d3y dx cubed equals 1 over x cubed, and in brackets d3y du cubed minus 3 d2y du squared plus 2 dy du. I haven't proved these, but I put these in, and I think sitting down and proving them will divert us from the main purpose of this particular little exercise, okay? I've written something in the footnote there which will help you to remember these a bit more easily should you ever need to use them. Right, so now work through an example, and here we have this equation here, x squared d2y dx squared minus 6y equals log of x. Okay, now the substitution x equals e to the u will transform this equation quite easily to this particular equation here. d2y du squared minus dy du minus 6y equals u, which if you looked at previous episodes, you'll recognize as a linear equation with constant coefficients. And I've just used the standard method of solving these, which first of all is to find the auxiliary equation, which is m squared minus m minus 6 equals 0. Factorize that. M minus 3 times m plus 2 is 0, giving m equals 3 or minus 2. And so the complementary function will be y b equals ae to the 3u plus be to the minus tu. And substituting back to the old variable, that becomes ax cubed plus b over x squared. So that deals with the complementary function. We now come to the particular integral. This is usually where all the hard work is. Okay? In this particular one, we'll try y equals b plus qu, and then differentiating dy du is b, and d2y dx squared, d2y du squared is 0. And then substituting back, we'll quite easily get the expression 0 minus q minus 6b minus 6qu is identical to u, and equating coefficients of like terms, we quite easily get q equal to minus 1 upon 6 and p equals 1 upon 36. And so the particular integral will be 1 over 36 minus u over 6, which, going back to the old variable, is 1 over 36 minus 1/6 log to base e of x. Okay, and the complete solution will then be y equals ax cubed plus b over x squared plus 1 over 36 minus 1/6 log to base ex. So that does the first example. We now move on to a second example, which is not dissimilar at all. Okay, and here it is, x squared d2y dx squared minus x dy dx plus y equals 4x cubed. Again, let x equal e to the u, and the equation will readily transform into this equation here, which is d2y du squared minus 2 dy du plus y equals 4e to the power 3u. The auxiliary equation is m squared minus 2m plus 1 is 0, which is a perfect square. So m minus 1 squared is 0, which means m is 1. And of course, we have a double root this time. Okay, so the complementary function yc will be a plus bu e to the u, which is, going back to the old variable, a plus b log x times x. So we got that far. So that's the complementary function dealt with. Now we come to the particular integral. So we'll try y of b equals some constant c times e to the 3u. And from that, when we differentiate, we'll get the first differential as 3ce to the 3u, and the second differential as 9ce to the 3u. And then substituting back, we quite easily get 9c minus 6c plus c all times e to the power 3u equals 4e to the 3u, which of course will easily give us 4c equals 4 and c equals 1. And so yp will just be e to the power 3u, which, going back to the old variable, is x cubed. Okay, and so our final solution will be y equals bracket a plus b log x times x plus the cube of x. All right, now I've put down some examples for you to practice with. Give you time to write them down. I've given the answers in red, and when we've done that, we'll move on to the footnote. So just pause for a minute. I'm still here. I'll keep saying that every now and then. I'm still here. We'll move on in just a few seconds. Okay, your 1 minute is up, so we'll just move on. The lettering in red are simply the answers to those questions. Okay, now footnote here. If we denote dy dx by d and d2y dx squared by d squared and so on, and at the same time denote dy du by theta, d2y du squared by theta squared, and so on, then if x is e to the u, we can, by using the chain rule of differentiation, get the following. X dy equals theta y. X squared d2y equals theta times theta minus 1y. X cubed d3y equals theta times theta minus 1 times theta minus 2y. x to the fourth d to the fourth y equals theta times theta minus 1 times theta minus 2 times theta minus 3y, and so on forever and ever. And I just hope that this will prove useful to you from time to time. Thank you for listening to this rather lengthy episode. Goodbye.